My name is Maurice, Ezeoke. I'm from the University College London. I'm also a onboard data handling engineer with the National Space Research Development Agency. Today I'll be talking about my work on oil sands exploration, initial measurement results. This is for the methodologies track. So essentially what I really want to bring about is the process by which we're able to characterize the radar cross-section, essentially. So I'll briefly cover introduction, talk a little bit about the theory, experimental measurements, then I'll conclude with a summary of results. So backscattering, which is what we're interested in, has existed for quite some time. In 1945, the Soviet inventor called Leon Theremin presented a gift to the United States ambassador in Moscow. He hid it in this great seal, but essentially once an incident energy was shown from across the street, it was able to pick up everything that was discussed in the ambassador's office. So I guess the NSA spying did not just start now. What we're interested in, however, is for terrain, the backscattering coefficient. It responds to several factors, such as physical factors, electrical factors, and there are a variety of scattering mechanisms, from the ideal specular reflection, which is like a mirror, all the way to the Lambertian reflection, which is what you probably see from terrain. And it responds to both sensor factors, like the frequency or wavelength of the EM radiation, and also the terrain parameters like how rough the surface is, the slope, orientation, and surface features. Our model is essentially like an S-parameter model. So there are three essential components. There's an incident energy, E-ing, a reflected energy, E-ref, and there's also that's energy transmitted. So what we're interested in is like the S matrix, but for our own case, we want to see it in the far field, and we also want to see it at different incident angles, because typically a satellite in space will be able to see, will be able to hinge on its axis to see the terrain at different angles. So how did we do this? That was an anechoic chamber. Our measurement system consisted of a horn antenna, and we put our terrain. You can see it's quite difficult to suspend terrain in the air. So I'll tell you how we did that. We put our terrain essentially in the air, and we had a horn antenna, a tripod stand, and just a vector network analyzer. So the samples that we looked at were beach sand, oil sands from Nigeria, or in Canada they call them tar sands or bitumen sands, 10mm pebbles, and also 40 millimeter gravel. Then we had what we call styrofoam PFB boxes. They have a dielectric permittivity which is 1.03, while the dielectric permittivity of air is about 1. So therefore it was essentially, allowed incident radiation come into the boxes, interact with the terrain, then reflect. Then for our far field distances, using the antennas we use, for 1 gigahertz radiation it would be about 0.5 meters. For 9.7 gigahertz it was 4.6 meters. But we put our terrain in 4.9 meters so that we avoided the reactive effects. So typically for the measurement campaign, we did our calibration. The vector network analyzer functioned as both the transmitting and receiving device. We looked at both horizontal transmit, horizontal receive, vertical transmit, vertical receive at these angles, 30 degrees, 15 degrees. Nadir image in that straight was 0 degrees, 90 degrees. Then we acquired about 60 data sets. In order to calibrate our measurements, we used dihedral, corner, and planar reflections. Results. So here we show the S11 results for the different terrain types. The first thing we see is that for 10mm pebbles and 40mm gravel, we see that there's better reflection in the upper C band. That's from 7 to 8 gigahertz, shown by the green, for horizontal transmit, horizontal receive. But because of some previous work we have done, we're actually interested in the behavior of oil sands in the 7 to 8 gigahertz spectrum, because the dielectric permittivity, when we measured it, has some kind of resonance effect. Then we also looked at the terrain at different incident angles, like I said, plus 30, minus 30. Although the measurements were taken at different times, the peak terrain reflectivity for both plus and minus 30 degrees indicated similar results, which shows that our measurement system and methodology was appropriate. Also, we saw higher reflectivity from the planar reflectors at X-band. So that green line you see there, this was plotted in MATLAB, is for the planar reflector, which is what you would expect for a monostatic configuration, showing that our calibration methodology was okay. However, a slight difference occurred at minus 30 degrees as when the antenna looked down, which was that the beach sand seemed to provide greater reflectance. It wasn't more than the planar reflector, that would have been a disappointment, but it was more than